In this video, we're going to talk about an important concept in calculus called limit. Calculus is an enormously powerful branch of math with a wide range of applications. What gives calculus the power and distinguishes it from algebra is the concept of limit. Limiting behavior occurs in a variety of practical situations. So think about speed limit. If there's anything where you have a cap, then that's a limit of some sort. We're going to take a look at lots of applications as we go through the course. Speed limit is one that I like to think of. So that concept of limit, what we're going to look at first is a limit as far as functions go and at a particular value of x. So first example, we're going to take a look at something you're familiar with, which is the graph of a straight line. Consider the function f of x equals 2x plus 5. Describe the function and find f of 3. So our function is a straight line. I've got it graphed to the right, and I did that by taking the y-intercept at 5 and then the slope. And then f of 3, if we substitute a 3 in, we get a y value of 11. Okay, so that's a matter of plugging in points, x values to get y values. Calculus concept is find the limit as x approaches 3 of the function f of x equals 2x plus 5. And this is the notation limit as x approaches 3 of 2x plus 5. The concept of a limit means that as the values of x approach 3 from the right and from the left, is there a value of f of x that's being approached? Calculus does not care if it reaches that point. It cares what the intended value is. Okay, so for example, the value that we're looking at, if x is 3, as we take a look from the left, smaller values of x approaching it from the left and approaching it from the right, we're going to look at values of x close to 3 on either side, and then see what the y values are, and then take a look and see if we can guess what the value of should be at 3. So to complete a table, we take a look at 2.9, 2.99, 2.999, values close to 3 coming in from the left, values close to 3 coming in from the right. So I type this into Desmos. We have f of x equals 2x plus 5, created a table, and as you put in 2.9, 2.99, 2.999, notice that the values get closer to 11. They're a little bit smaller. When x is greater than 3, 3.001, 3.01, the values are a little bit larger than 11. But the intended value for 3 is 11. So the x values close to 3 give us a value for the output that's close to 11. So the limit of a function f of x is the value which the function approaches as x approaches a given value, written in this notation. The limit as x approaches a of f of x is equal to L. And the answer, L, is basically the y value. Okay, I'm going to come back to important ideas about limits after we take a look at some examples. So example 7, find the limit of a function as x approaches 2. So in that linear function, we could just substitute in a 2 and we would know what y is. But in this function, if we substitute 2, we get a 0 in the denominator, which is undefined. So we can't just substitute a 2 and find a limit. So what I'm going to do instead is take a look at this particular function. I'm going to type it in the calculator on Desmos and then put in different values and see if I can guess what the y value for 2 should be as you look at values on either side. So when you type it into Desmos, you can use the, I think I can just do the fraction bar. I'm going to use parentheses and type in the numerator, which is 2x squared minus 3x minus 2. I'm going to keep parentheses around it and then divided by, and then type in the denominator, which is x minus 2. And then what I want to do is put in the values in this table. So let me get rid of the table. How you create a table is you add table, and then make sure that you label this, instead of y1, call it f of x1. Then when you put in values for x, it will automatically calculate your values of y. So I want to know what happens, the limit, as x approaches 2. So I'm going to put in these values on the left-hand side of 2 and to the right of 2, and see if I can guess what the y value should be at 2. So I've got 1.9, 1.99, 1.999. It looks like it's getting close to 5. If you put in a 2, you'll get undefined. 2.001, 2.01, and 2.1, just to put all the values in. So as x approaches 2 from the left and from the right, numbers smaller than 2, larger than 2, the values of y approach 5. So a limit is, when we say it doesn't care if it reaches the value, it's undefined. This function is undefined at 2, but the y value, the intended y value, as x approaches y from the left and right, is 5. So this is called evaluating numerically. By just actually putting the values in and see what happens. So the numeric approach, you take the table of values, it looks like the limit as x approaches 2 is equal to 5. The algebraic approach, if you notice, our graph was a straight line. So how did that happen? If you can take the algebra expression and simplify it, this 2x squared minus 3x minus 2 actually factors. X in the first spot, 2x. And then I know that x minus 2 is going to be one of the factors because it's going to cancel. 2 times 1 is 2. In order to get a negative 2 here and a 3 here, I need to have a positive value. Double check your factoring. X times 2x is 2x squared. Outer is plus 1x minus 3x. Yep, minus 4x is negative 3, negative 2. These factor. You can simplify the function. Then check and see, can you take the limit as x approaches 2 of the simplified function? And the answer is yes. The limit as x approaches 2 of 2x plus 1, you can substitute a 2 for the x, and we end up with 5. So that's called an approach, an algebraic approach. You factor and then simplify if possible. So back up here, if you ever wondered how you get a hole, a graph of a line with a hole in it, the graph of this line is 2x plus 1 of this function, but it has a hole at 2. So important ideas about limits. If you can, first of all, to find a limit, see if you can substitute x into f of x to get y, to get your limit. If that doesn't work and it's undefined, see if you can simplify using algebra. And then substitute x into f of x to get the limit, because the limit is the y value that it approaches. If neither one of those work, 3, make a table of values and solve numerically. So there are 3 important ideas about limits. To find a limit, check and see if you can substitute x into the function to get the limit. Simplify using algebra and then substitute to get the limit if you can't do that in one. If none of those work, use a table of values. Okay? So I'm going to take a look at example 10. Find the limit as x approaches 4 of x squared minus 7. So the question is, what does y approach as x approaches 4? See if you can substitute 4 directly in. In this case, we can. 4 squared is 16 minus 7. So the limit is 9. As x approaches 4, y approaches 9, or the function approaches 9. The next example, find the limit as t approaches 2 of t squared minus 4 over t minus 2. If we substitute 2, it would give us 0 on the bottom, so we can't substitute directly. So then, try to simplify. Factor the numerator, that's a difference of squares. It becomes t plus 2 times t minus 2 over t minus 2. These cancel, and we're left with t plus 2. So then try to find the limit as t approaches 2 of your simplified function. Now it works. Now I can substitute a 2 in there, and I end up with 4. Okay? So the graph of this would be a straight line, t plus 2, with a hole at the coordinate 2, 4. All right, we want to take a look at this example where the limit does not exist. In trying to find the limit as x approaches 2 of 1 over x minus 2, we can't substitute 2 directly. It doesn't work. We get 0 in the denominator. We can't simplify it, so we're going to take a look and see what happens numerically. So in Desmos, I'm going to type in 1 over x minus 2. Notice I have the graph, but I'm going to use this to for the values, to get the values in the table. And we want to find the limit as x approaches 2. So over here, I'm going to put in 1.5, 1.99. I'm going to put the values in and see what happens. So as we put in values closer to 2, my values are getting bigger. Okay. Now on the other side of 2, 2.001, 2.01, now we notice our values are starting larger, getting larger when we approach from that side. So if I were to put in a value of 2, I certainly get undefined, but on either end of it, they're not approaching the same number. They're going in completely opposite directions. So if they're going in completely opposite directions, the limit does not exist. So what we would write is that limit does not exist, DNE, which means does not exist. So you have to be approaching the same number from the left and from the right to be able to fill in a value for 2 if there is a limit. It should be approaching the same y value either direction. All right, last idea is taking a look at limits as x approaches infinity. So we want to find the limit as x approaches infinity of x squared plus 1 over 2x squared plus 3. If x approaches infinity, we certainly can't put infinity in there. So what we do is we take a look at values of x that are larger and larger and see if the values of y approaches a particular number. So again, you can use table function on a graphing calculator or on Desmos. And I want to put in the function x squared plus 1 over 2x squared plus 3. It's a crazy looking function. So then I want to make sure I get in values that are approaching infinity. So I need to go to that table in Desmos and put in the numbers 1, 10, 100, 1,000, and then take a look, 10,000. And what are the y values getting closer to? The larger the x values are, the y values look to me like they're approaching 0. Let me make sure I have the right function in there. X squared plus 1, 2x squared plus 3. Oh, I need to put x squared plus 1. Sorry about that. There we go. So now the graph changed and the values changed. I just had to get the right graph in there. So as the values get larger, notice on the graph, the y values, as x approaches 2, the y, or infinity, the y values approach 0.5. Matter of fact, 10,000, it's so close to 5, it's rounded it to 0.5. So the limit, as x approaches infinity, for this question, is equal to 1/2, or 0.5. Okay? And that would also be called a horizontal asymptote. All right, last example. A 5 ohm resistor and a variable resistor of resistance R are placed in parallel. The expression for the resulting resistance R sub t is given by R sub t equals 5R over 5 plus R. Determine the limiting value of R of t as R approaches infinity. So this is asking us to find the limit as R approaches infinity of this function. So as capital R, the variable resistance R, as R gets larger and larger, then what happens? So let's do this numerically. So I'm going to go ahead and type it in, 5R over 5 plus R. I'll just use X. So I've got 5X over 5 plus X. So the advantage to using Desmos is you have the table still here. So as X gets bigger and bigger, it looks like the Y values, or in this case the R sub t values, get closer and closer to 5. So the limit is equal to 5. So that's the limiting value of R sub t.